In this video, we will learn how to predict products for double replacement reactions, specifically taking advantage of solubility rules. Now, a double replacement reaction is where two anions or two cations switch places. So for example here, D and B switch places, and so we get two different ionic compounds. And what we need to be produced, we need a couple different things, just one of them, but we need a solid, liquid, or gas to be produced in order for this reaction to actually occur. Now, the only liquid I can think of that you'll see on a regular basis would be water, and that we can think of as HOH, H2O. And then common gases that may be produced would be CO2, SO2, carbon monoxide, nitrogen dioxide, and really that's all that comes to mind. We don't seem to see gases too much, but that CO2 we will actually see probably more common than not. When we use solubility rules, I use this chart, and this is a common chart. I know I use this in AP Chemistry as well, so if you decide to take AP Chemistry, this chart will not be anything new. And what solubility rules are just general guidelines to be able to tell if something is going to be soluble. That means it will be aqueous, and that means it'll dissolve in water, or insoluble. And if something is not soluble or insoluble, that means it will be a precipitate, meaning the reaction can occur. If we get two aqueous products, and maybe we write this down because this is some important information, two aqueous products means no reaction. Okay, and that means that a reaction actually does not occur. Okay, and how you read these is that if I have a nitrate, a chlorate, an acetate, no matter what they're paired with, they are always soluble. Additionally, if I have an alkali group 1A cation, or ammonium, whatever they're paired with in an ionic compound, they will also be soluble, meaning they will dissolve. And so what that means is that these will be aqueous, and for rule number 2, that will be aqueous. And number three specifically talks about halogens, the chlorides, bromides, and iodides, and those will always be soluble except with silver, lead, and mercury. And the way, if you want to know a way that I use to remember that, I remember AP and honors classes. So silver, lead, and mercury. And sulfates will always be soluble, but if we have barium sulfate, lead sulfate, mercury sulfate, or calcium sulfate, it'll actually give us a precipitate. And the way I remember those exceptions is bad lead, hungry cats. I don't know why that works for me, but it does. And then everything else pretty much is going to be insoluble. And so if I look at hydroxides are very not soluble, except if they're with an alkali or an ammonium. There are 3 exceptions, and I remember those. Calcium, barium, strontium, CBS, just like the TV station. And then sulfides, carbonates, chromates, phosphates are not soluble unless they're with an alkali or an ammonium. And that goes back to rule 2, because group 1A and ammonium, they're always soluble, so it doesn't matter what you put it with, they're always going to be soluble. and then oxides, which are I'd say they're not very common for regular chemistry, but they're not going to be very soluble. So let's go through some examples and see exactly how this works. So in number 1 here, I'm given zinc acetate and cesium hydroxide, and they're going to react, and hopefully when I write this out, you will see that it will in fact be a double replacement reaction. The way I go through and do this is I first write my ions, because that will help me make my ionic compounds. And you may not be able to see it here, but I'm just looking at a periodic table right in front of me. And so zinc acetate, Zn, C2H3O2 with 1 minus charge, and I don't need the charge there. Need 2 of those, plus cesium hydroxide. And what I will form is I've got to see if I'm going to form a solid, liquid, or gas. And so I need to first predict the products. I'll take zinc, and it will bond with hydroxide potentially, so we'll get zinc hydroxide. And our other product would be cesium acetate, and that would be C2H3O2. And to go ahead and get my states of matter here, I'm going to do it for everything. Specifically, I need to know my states of matter for my products to know if I have a reaction. Okay, so in zinc acetate, I have an acetate, so I know that that's a rule, and acetates are always soluble, so that looks pretty good. So that will be aqueous if something is soluble. I can go ahead and put aqueous over here for that cesium acetate, because acetates are always soluble. And I've got cesium and hydroxide here, so I'm going to go ahead and I'm going to look at the rules for hydroxide just to save me a little bit of time, because I've got hydroxides in these last 2. So that would be this rule number 5. Hydroxides are not soluble. They are just not soluble, and so that helps me out. However, if I have group 1A, or if I have ammonium and then one of these CBSs, then it actually will be soluble. So let's go down and look at this. I've got cesium hydroxide. Cesium is in group 1A, so that will be aqueous. And then I've got zinc. Zinc is not in group 1A, zinc is not ammonium, and zinc is not calcium, strontium, or barium. So that actually is a solid, and so this reaction will occur. To finish this off, I'll go ahead and I will get this balanced. Okay, so number 1 looks good. Let's look at number 2. I've got chromium 3 bromide, and I've got sodium nitrate. So chromium 3, that will be Cr plus 3. Bromide will be Br minus 1. Sodium will be Na plus 1. And nitrate is NO3 with a minus 1 charge. Okay, so let's get this going. I've got CrBr3 with some state of matter. We'll figure that out here in a second. Plus sodium nitrate with some state of matter, and those 2 will react in a double replacement reaction where chromium will go hang out with nitrate, and so I'll get CrNO3 with some state of matter plus sodium bromide with some state of matter. And so let's go ahead and look at this. I'll go ahead and look at this solubility of bromide. So that will be these 2, and that would be rule number 3. So those guys are always soluble unless it's silver, lead, and mercury. And in question number 2, I don't have any silver, lead, and mercury. So what that means is that this will be aqueous. And then in this next one, I'll look at nitrate. I know there's a rule for nitrate, so I'll go back up. And nitrates are actually always soluble, so that means that both of those guys, those will be aqueous. And with that, I've got 2 aqueous products, and that means that this will be no reaction. So this is actually, we can write above the arrow, no RXN. I'm not going to worry about balancing because the reaction does not even occur. Let's look at number 3. We've got silver nitrate and potassium phosphate, and those guys are mixed. Silver is Ag with a +1 charge. Nitrate is NO3 -1. Potassium is K +1. Phosphate is PO4 3-. And so I've got AgNO3. We just saw in the previous problem that all nitrates are aqueous, so I can go ahead and do that. Plus potassium phosphate, that'll be K3PO4. And potassium is in group 1A. In group 1A, it doesn't matter what group 1A is paired with. Group 1A ionic compounds will always be aqueous as well. One common mistake from some chemistry students is that they'll say, oh, I've got 2 aqueous reactants, so that means no reaction. But that's not at all what we're concerned about. We're concerned about what the products will be. So we've got to predict the products first. So we don't know just yet if the reaction occurs. But I know silver is going to go hang out with phosphate, and so we're going to get Ag3PO4 with some state of matter, and I don't remember that one off the top of my head. And then we're going to get potassium nitrate, KNO3, and I know that will be aqueous because it's got potassium, which is group 1A, and it also has nitrate, and nitrates are always soluble. So I need to look at the rules probably for phosphate. My guess is phosphate has its own set of rules. And if we look at number 6, phosphates are going to be not soluble, meaning that they'll be solid, unless it's with group 1A, which silver is not, or ammonium, and silver is not ammonium. So we can go ahead and make this a solid. And so this reaction does occur. And to top this off, I can just balance it as such. And okay, that one looks good. Let's look at number 4. We've got copper bromide. And this is specifically copper 2 bromide, so we have Cu +2, Br -1, Al +3, and then Cl -1. So I get CuBr2 plus aluminum chloride, and with some state of matter. And I remember that halogens are always going to be soluble, so those are those guys, unless it's APH. AP in honors classes. The A stands for silver. I don't have silver here. The P stands for lead. I don't have lead here. And the H stands for mercury, and I don't have mercury here, so I automatically know that these are going to be aqueous. And then I'm going to flip them, so copper's going to go hang out with chlorine, and so I have CuCl2. Again, halogens. That's not paired with silver, lead, or mercury, so that I know that that will be aqueous. Plus aluminum bromide, AlBr3. Halogens are always aqueous unless it's paired with silver, lead, and mercury, and aluminum is not one of those, so that's aqueous. So I can stop now because I have 2 aqueous products, which means no reaction actually occurs. I want to look at, let me flip through. I want to find one that's a little bit different, and I want to look at number 11. And on number 11 we have iron 3 sulfate, and so that will be Fe with a +3 charge. Sulfate is SO4 with a 2- charge, and that's going to react with potassium sulfide. Make sure when you read this, you read it as sulfide and not sulfite. I know that that's a small distinction, but we got to make sure we catch that. And so I have Fe2SO4 3 plus K2S. I automatically know that K2S, or potassium sulfide, will be aqueous because potassium is in group 1A on the periodic table. And then I remember my solubility rules a little bit, and all sulfates are going to be soluble unless it's bad lead, hungry cats. So that's BA, PB, GCA, and iron is not in that list, so I know that that will actually be aqueous. And I'm going to get iron pairing up with sulfide, and so I get Fe2S3, and I don't know that state of matter off the top of my head, plus potassium sulfate, and that has potassium, so of course it will be aqueous. And I've got to go back and look at my solubility rules for sulfides, so I'll scroll up here, and sulfides are actually always going to be not soluble unless they're paired with group 1A, which iron is not, or ammonium, which again iron is not. So I know that that's going to be not soluble, which means it will be a solid. So I can go through and just top this off and get this one balanced. And so what I'll do is I actually look at it and I say, wow, this is already balanced. Okay, so this one is actually done, and yeah, we got lucky.